I will start with just an introduction of us, who we are. So it's me, Anders Florén, and then Maria Zambrotta from Italy, and Iro from Greece. And we are chemists or borderline chemists. Iro is actually a physics teacher, but we were focusing on the chemistry and things that you can do at the lab. Because what we wanted to focus on is bioplastics, and then wool and cement. And these are things that are that are like unsustainable the way you use them. Cement production is unsustainable. Wool is an old material that is discarded nowadays, and plastics can be recycled. So we focused at different activities that you can do with your students at the lab. So we needed a name for this. And then after a small discussion, Iro had a good idea, making it like the 3 R's, which is to reduce and reuse and recycle things. And I will turn over to Iro, who will talk about the materials that we have.
Yes, so hello from me also. So we began with some introductory materials for our unit in order to combine all the different activities that we're gonna talk to you about in a few moments. So we have some introductory material in order to introduce what the 3 R's are to your students, and they are in a form of a questionnaire, and there are activities in interactive activities like an interactive video, and there are also ideas about how to involve the students in with the community. For example, this is an example of a beach cleanup. So after the introductions of the 3 R's with different materials that one can use, we have 3 separate units. The first unit that I'm going to present has to do with bioplastics, and the second unit that Maria developed is exploring wool, and the third unit that Anders developed is cement production. So each one of them it can be taught in any order, so you can teach all of them in any order, or you can just pick one that fits best to your curriculum. So beginning with bioplastics, again, the questions that we thought about, that we wanted to introduce to our students is, can we live with a world without plastic? Can the 3 R's approach combat the escalating plastic problem? And are biopolymers a solution for a sustainable future? So we developed 2 different activities. One activity that is addressed to elementary students, and another activity that is addressed to high school students. So again, we have other introductory activities for bioplastics. You can find all of them in the web page, like games and interactive presentations about the history of plastics, or what are the different kinds of plastics. And other activities like this, an article where we have questions where you can use for the classroom. So the first activity that is addressed to elementary students had to do with production of plastic from lactate. It is actually a classic experiment where you can produce a kind of plastic from milk. You just have to use milk and hot milk and with vinegar, and then strain it, and then you have this bioplastic produced. So we use the storytelling technique and told students a story, which might be actually a real one, how this plastic was discovered. And we say that it all started with a cat, a clumsy cat, where it lived in the lab of Mr. Spittler, and the cat dropped accidentally the vinegar that was on the table in her bowl with milk. And the other morning, the scientists saw that this had happened, and that's how the first plastic from milk was discovered. So we give all materials and all instructions about this, how to do this lab activity. And so we did that for actually during COVID, we tested this. So we had a lot of kids, they were third grade elementary students that performed these experiments in their home kitchens. So in order to make it also more approachable to these smaller ages, we asked them that to use the plastic that they produced to make ornaments for the Christmas tree or some presents for their parents. And they had a lot of fun doing this. So we also tested this unit for this activity for older students, like fifth or sixth grade of elementary school. But there we focused on the more inquiry-based method. So we asked the students what would happen if we had a different kind of milk, if we used soya milk. Would we have the same result? Or what would happen if we would have different temperatures of the milk? If we had cold milk or another temperature of the milk, would we have the same result? So we focus on the inquiry-based method for that. So for the older students, we focused on recycling PLA, polylactic acid. So we found a protocol that recycles PLA cups, plastic cups that are made from PLA. It's from Beyond Benign University that has this protocol. And then we thought that we could apply this to our 3D printing material that we had left over from all the work we're doing with our 3D printers. So in our school, this is a problem because we have 3D printers that students use, and we have a lot of failed prints or a lot of parts from the scaffolding of the 3D printers. So we have boxes of plastic in the lab, which we don't know what to do. So actually, the filament of the 3D printers is made from polylactic acid, and we tried to apply the Beyond Benign protocol for these filaments. So it is a simple method, and I'm just going to finish my presentation just showing you a video that one of my students make, which explains the process. So 3 basic steps of the experiment. And we did this experiment. We tested it we did it for the cups, and we did it for the materials from the 3D printer. And then we also compared if we had a similar result with these two. So it's a simple hydrolysis, actually, of the PLA. And all steps of the procedure can be found in the website with all directions, and also this video that shows step by step what we did. And I'll just move it a bit further, just to say that we also combined it with the biology part. We tested if our solution could actually clean the benches, and we did some swap tests and checked if our solution was good enough. So that's from my part, Maria.
Thank you, Iro. Thank you, Joanna. I would explain why we decided to work with the wool and show you my part. So my part is related to the wool. A few years ago, I met a researcher from CNR that was involved in the study of the wool. So I can, for the first time, I met the problem because with the use of new materials for clothes or blankets, wool is being used less and less. But sheep still have to be shared to survive. So the disposal of wool is a problem, is a big problem. We try to understand with the student the possibility to recycle the wool. And we know that we can recycle the wool using for example, an acoustic isolation or thermal insulation. But my idea is to explore the chemistry of wool and do some activities to understand the chemistry of this new material. Okay. So the activities, we have lots of activities. Labs activity are introductory activity. On the website, you can find some introductory materials, for example, videos or other to read, to discuss and brainstorming with the students. The first lab activity is in using a microscope. You can explore the fiber and compare the wool fiber, so natural fiber, and then a synthetic fiber. So you can see on the natural fiber, the wool, and on the right of my screen, the rayon, that is a synthetic fiber. We have also produced sheet that can help the student to find the solution, to explore the photo and try to understand the differences of the fibers. After this, the first laboratorial activities and chemistry labs. This is a simple activity, is the extraction of the keratin from the wool using the hydroxide. It's simple, but it's better to use the wood for the smell of the keratin, of the solution. And so, and you can use this activity also in the lower class or in the higher class, because you can introduce this work in don't know, the extraction, or only related to the biochemistry of the wool. So you can choose a relation with your curricula. Other possibility is to use different chemicals to observe the results of flocculation, so students can understand what is the difference in using different kind of solution or different kind of chemicals, and what is the flocculation of the proteins, for example. On the website, you can see all the protocols to do this activity and the video to show the activities. The last but not least is to extract the keratin and then produce the hair conditioner. Using the keratin will be dry and then used with glycerol or other emulsionant to create the hair conditioner. With the younger students and without use of hydroxide, you can try to use natural colorants to dye the wool. So for example, example, the red garbage and curcuma to obtain a pink wool or yellow wool. And last activity is explore the use of wool for the water pollution, because the wool has the ability to absorb and recover the metals from the water. So you can show how these happen. And then, for example, here you can see sulfate copper solution, and the wool will be soaked in the solution, and then using a colorimeter or using a spectrophotometer or compare the color with the solution, you can see the ability of the wool to recover the metals. Thank you very much.
Thank you very much. I will talk about cement, and I will present some lab work, and this is available on the homepage, and you can see it yourself. So I will mainly talk about the chemistry, which is like interesting behind cement. So why cement and concrete? Let's see. So concrete is a big thing. I mean, concrete is like the second largest commodity that we are buying and selling. Number one is water. So it's like a lot of stuff. And we are all consuming concrete, a lot of it, even though we don't know. As like Swedish taxpayers, we're paying for roads and you know, all this stuff. So that means that me as a citizen consume like somewhere like 1.5 ton of concrete every year, which adds up to a lot, because a lot of this carbon dioxide, which is released in the production of the carbon of the concrete, it adds up to much more than flying, for instance. So if I take a plane to France, I think it's like I made some calculations depending on how big the plane is and this stuff, that maybe it's I can take somewhere between 3 to 5 trips to Paris, just releasing the same amount of fossil CO2 as the amount of concrete which is used. So this is important to explain to the kids, because the kids don't know about this problem. They think that the problem is flying, or the problem is only cars and stuff. This I will talk about a little bit later. It's the release of carbon dioxide, and this is from the lab material that you can look at later on. So essentially, we're working with this calcium carboxide, which is releasing fossil fuels. And this, if you use limestone, this was taken up by organisms that lived like 100 million years ago or something like that. And that means that we are releasing old carbon dioxide. So the idea was that how can we do this without releasing old carbon dioxide? Can we use something else that has just fixated the carbon? And of course you can, if you use the same material, which is just mussel shells. So because limestone is made from shells. So that means that we are using mussels that lived very, very recently. So this is what we are working with. And first I want to just show some chemistry, because the chemistry is in the work material, which is like red text and you can read it. But let's see, I want to share my screen, because I know that you all love chemistry, and who doesn't? So The chemistry behind concrete, you have calcium carboxide, and you heat this thing, and then you get something which is called like quicklime or calcium oxide, and CO2 is released, and this is stuff like fossil fuel. Also, you get some stuff is released from the heat when you heat this. And then you add water to it, you get slaked lime or essentially calcium hydroxide. And then this will harden into something which is mortar. This is not concrete, because for concrete you need other stuffs. So this is exactly, and this is more or less what we do in the lab with the kids. And the thing is that when you produce this thing, the released carbon dioxide is the same amount is taken up by your slaked lime when it's hardened to become mortar or, well, cement, something like that. So the Romans, they knew how to make concrete. The same thing, you take calcium carboxide, they didn't use shells, they used limestone. You get the quicklime, you add this to, you need volcanic ash, and volcanic ash has the right structure because it's formed at very high temperature. And then you get wet concrete and it will harden as normal concrete. So we don't use volcanic ash, and this was forgotten. So what we use nowadays is we just take limestone and sand, we heat it a lot, as hot as it gets in the volcanic eruptions. So you get this dry concrete, add water to it, and it will harden. So the thing is that we are working in another project is to make essentially the same thing from limestones and from mussel shells, and this silicon oxide that you use, you get ash from biofuel, because when you burn things like rice husks or something like that, it has up to like 4 or 5% of silicon oxide. So, and in a big power plant for biofuel, it will get really, really hot. So it will have the right structure, and then you can make concrete from it. So this is like the chemistry. Okay, so what I wanted to say was some comments about the material. So first, you need to have mussel shells, and you can have a discussion of where are these coming from and what are they about. And also, let me skip one slide because I know the time is almost up. If you want to do this, you need to somehow dry the mussel shells before you take them to your lab, because they will get very smelly otherwise. So you dry them in your own oven at home. You grind them up like this to a fine powder. And this is important if you're doing the same thing, that it needs to be really fine. You can't use lumps of this stuff. Then you can check some interesting chemistry. You can see that this powder does not affect the pH, but is affected by acidic solutions. So it will bubble and produce carbon dioxide. So the important thing here is you can use differential weighing. So you can weigh up some stuff, and then you can heat it, and then you weigh it afterwards. And you can monitor the amount of carbon dioxide which is released. You can actually calculate this, yes, with stoichiometric things. You can use any form of heater. But if you're using this, which is like a gas heater, you can also wait before heating, after heating. Then you can calculate how much energy you use and how much carbon dioxide was released. Because this one contains like propane, and you can calculate how many grams of CO2 which was released. Let's see. So anyway, then at the end there we also have some interesting thing, because when you make the slaked lime, it's actually it has like inverted solubility. So it's the more warmer it is, because it's an endothermic reaction, the more warm it is, the less soluble it is, because it comes from this Le Chatelier principle. So it will actually be very, very hard to control. So this is interesting chemistry that you can dwell on if you would like to. So and then also you can make from your from the stuff that you get, this carbon, this calcium oxide and calcium hydroxide. You can study the pH, how it behaves when you add acidic solutions to it, and it's like a lot of interesting chemistry in this. So thank you for your attention.